So here is kind of a practice exercise on finding limits at certain numbers. So we're going to go through, there's a number that is highlighted on the x value on this very crazy looking graph, and we're going to look at the limits at each one of these numbers. So first starting with -6. So in this case, as we get closer to -6, we can see that there's an asymptote at -6, and on one side of the asymptote it is increasing, and on the other side of the asymptote it has been decreasing as you approach the asymptote from the right side. So this is a case that whatever this function is, as the limit approaches -6, since it's approaching two different numbers on both sides, or actually it's increasing and decreasing indefinitely on both sides.
The limit does not exist. The limit does not exist.
X equals -4. So if we look at x equals -4 and we try to find the limit of x equals -4, we would also say the limit does not exist.
The limit does not exist.
Because it is approaching different numbers on both sides. So actually x equals -4 is defined at this point. It's defined to be approximately 2. However, since it doesn't approach 2 from the right side, it's actually approaching a number that's higher than 2. It's actually approaching 3. Even though f of -4 does equal 2, the limit as f approaches -4 doesn't exist because it is approaching different numbers from both sides. When we go to the x-axis, in other words, we're seeing when f approaches 0. So as f approaches 0, notice that as we come in from the right side, let me erase some of the things I got here. As we come in from the right side, as x approaches 0, that we do get an answer of approximately 3.44. I believe it says up there it's 3.4. As we approach from the right side, it is also approaching that same open circle, which would be 3.4. So the limit as x approaches 0 is 3.4, even though f of 0 is defined. Notice that we do have a dot there when x is 0, that y, or f of x, is actually 2. So even though f of x equals 2, or f of 0 equals 2, the limit as f approaches 0 is actually 3.4. At the asymptote located at 3, right here, that asymptote. At the asymptote at 3, notice that we are dropping on both sides. So it is going to continue to drop forever and ever and ever on both sides. So what we would say is that the limit is approaching -infinity as x approaches 3, but it's not approaching any certain number because -infinity isn't a specific number. So you might say that f of x is approaching -infinity, or you could say
the limit does not exist.
And it's going to depend on the problem that we're doing and what we're trying to solve. And we're going to learn that as we move forward in calculus. X equals 4. As x equals 4, it's a very similar situation as we had when x approaches 0. It's approaching 1 from the right side, a y value of 1 from the left side, and it's approaching a y value of 1 from the right side. So even though f of 4 is not defined, there we go, whoops. Even though f of 4 is not defined because we have a open circle there, we have a hole there, the limit as x approaches 4 is actually 1. And then finally we have as x approaches 6, do some erasing here. So as x approaches 6, it is approaching the same number from both sides, and in this case the limit as f of x approaches 6 is equal to 2, and that's actually what f of x equals because we do have a dot there, which means f of 6 actually is defined. Okay, so let's practice some techniques on finding limits. So the first one is find the limit as x approaches 3 of x squared minus x minus 1 over the square root of x plus 1. The first thing we're going to do, check for direct substitution. Can I just plug 3 in for x and get an answer? So when I plug 3 in for x, I'd have 3 squared minus 3 minus 1 over the square root of 3 plus 1. And in the denominator, I would have the square root of 3 plus 1, which is 4, and that would equal 2, which means I don't have 0 in the denominator, which means we're going to be able to define this one fairly quickly because we didn't get 0 in the denominator. In the numerator, I would have 9 minus 3 minus 1. 9 minus 3 is 6, minus 1 is 5. So the limit as x approaches 3 equals 5 halves. Example 5, same thing. Find the limit of that function, x squared plus x minus 6 over x minus 2, as x approaches 2. So again, we will try a direct substitution first. 2 squared plus 2 minus 6 over 2 minus 2. And you can see that when I have 2 minus 2, I'm going to get 0 in the denominator. And I'm actually going to get 0 in the numerator too. I'm going to have 2 squared, which is going to be 4 minus 2 plus 2 minus 6. That's going to be 0 over 0. Mathematicians refer to 0 over 0 as an indeterminate form. Zero over 0 does not help us at all in finding limits, and that often happens when we try to do a direct substitution. So direct substitution is not going to work because we get 0 over 0, which is that indeterminate form. So we have to try some other techniques. Now on this particular one, if you notice we have a trinomial in the numerator, let's try factoring that trinomial and see if we can do that. So x squared plus x minus 6, that actually factors into x plus 3, x minus 2. And the x minus 2's will cancel, leaving us with just x plus 3. Now that we know that it just simplifies to x plus 3, I can do a direct substitution and replace that x with a 2. I get 2 plus 3, which will equal 5. So the limit as x approaches 2 is equal to 5, even though doing direct substitution with the original problem yields the indeterminate form. In this situation, the reason it is it's one of those situations where we actually have a hole in the graph. So since we would graph x plus 3, you would go up 3, place a point there, go up 1 over 1, then very quick sketching of a graph. But as x approaches 2, we would have a hole in the graph right there. That's kind of a big hole, but hopefully you get the idea. That's what the graph would look like. Let's look at example 6. Find the limit as x approaches 4 of the square root of x minus 2 over x minus 4. So again, if we try to do direct substitution on this one, we would have the square root of 4 minus 2 over 4 minus 4. That would give us 2 minus 2 over 4 minus 4. That gives us 0 over 0, and we get an indeterminate form. So direct substitution doesn't help us out a whole lot. But what we can do in this one is do a technique called rationalize the numerator. Yes, rationalize the numerator. So this kind of blows new calculus students' minds a little bit. And the reason for that is you've been told pretty much your entire algebra life that you should not leave a radical or a square root in the denominator. It's not allowed. And we did rationalize the denominator to take care of that. But right now we're going to do rationalize the numerator, and we really don't care if there's going to be a square root in the denominator or not. And the reason for that is that we are eventually hoping to plug in a number in for x. And when we do that, that will actually help us find the limit that we're looking for. So don't worry so much if there is a radical in the denominator. We're not going to concern ourselves with that, because eventually we are plugging in numbers in for those square roots, variables in the square roots. So to rationalize the numerator, we're going to need to multiply it times the conjugate. If you recall from algebra, the conjugate is the same terms, but a different sign in between. So the conjugate of the square root of x minus 2 is the square root of x plus 2. So we multiply it times the square root of x plus 2 over the square root of x plus 2. Square root of x times the square root of x equals x. Square root of x times 2 is 2 square root of x. Negative 2 times square root of x is negative 2 square root of x. Negative 2 times 2 equals negative 4. And I'm actually not going to bother to multiply the denominator. I'm just going to leave it as a binomial pair. And you'll see why here in a second. So the 2 square root of x minus 2 square root of x, they're going to cancel each other out. And that's going to leave us with x minus 4 over x minus 4 square root of x plus 2. Now you can see that we have an x minus 4 in the numerator, x minus 4 in the denominator. Those are going to cancel each other out. That means we are going to be left with a 1 in the numerator and the square root of x plus 2 in the denominator. Now when I plug in that 4 with direct substitution, I have 1 over the square root of 4 plus 2. That'll become 1 over the square root of 4 equals 2, 2 plus 2, which equals 1/4. So the limit of this function as we approach 4 is 1/4. On example number 7, and kind of ignore that graph down there. I don't want to spoil the ending for you, but the limit as x approaches 1 of that function. So again, always try direct substitution first, but when we do direct substitution, we get 1 squared minus 2 times 1 plus 1 over 1 minus 1 to the third power. 1 squared is 1. Negative 2 times 1 is negative 2 plus 1 over 1 minus 1 to the third power would be 0 to the third power. 1 minus 2 plus 1 is 0 over 0. Indeterminate form, we should not try direct substitution immediately. So let's try some of the techniques that we've learned so far. One of those techniques is that we can factor in the numerator and hope something cancels out. And this one does actually factor. It factors into x minus 1 over x minus 1 over x minus 1 to the third power. X minus 1 is x minus 1 squared over x minus 1 to the third power. And this x minus 1 squared will cancel out with 2 of the x minus 1s in the x minus 1 to the third power, which will give us 1 over x minus 1. Now in this particular case, when we do x approaches 1, we get 1 over, so I'm replacing the x with that 1, we get 1 over 1 minus 1, which gives us 1 over 0. Now, this is not an indeterminate form. We get 1 over 0. If we look at the graph now, the graph, you can see when we simplify this, it's actually a rational function. It's the rational function y equals 1 over x minus 1. So if you remember from the previous chapter what a rational function looks like, on one side of the rational function, it is decreasing indefinitely. On the other side, as it approaches 1, as the limit approaches 1, it's increasing indefinitely. And where x equals 1, if you recall how to graph these functions, there's actually an asymptote. So, since it is approaching an incredibly small number from the left side and an incredibly large number from the right side, since it's approaching negative infinity from the left side and positive infinity from the right side, we can again say
The limit does not exist. The limit does not exist.